The universe began as a silent, empty stage. What sparked the very first chemical reactions that set the stage for everything we see today? By the end of this journey, you will uncover 30 mind-bending theories explaining how the cosmos went from a barren void to a chemical wonderland. We will explore whether the first molecule was forged in the heart of a star or born from the ghostly grip of dark matter. What single force could have guided the formation of molecules essential for life itself? That silent stage did not stay empty for long. In the aftermath of the Big Bang, the entire universe was a roiling, unimaginably hot cauldron. This was the primordial soup, a fundamental concept for understanding our cosmic origins. For a brief moment, the universe was so dense and hot that even atoms could not hold their form. It was a chaotic sea of particles, a fundamental broth. But as this cosmic pot expanded, it also began to cool, and in that cooling, a profound shift occurred. Protons and electrons, once wildly free, began to find one another, combining to form the very first atoms. These were almost entirely atoms of hydrogen, the simplest element in existence. Yet, single atoms were not enough to begin true chemistry. The next pivotal step was for these solitary hydrogen atoms to find partners. In the cooling fog of the early cosmos, they began to bump into one another, but a collision is not a connection. They needed a way to stick together. The key was a third party, a catalyst. When two hydrogen atoms met in the presence of a solid particle, like a speck of cosmic dust, or exchanged a particle of light, a photon, they could form a bond. This was the birth of the hydrogen molecule, known as H2. It seems almost too simple to be significant, a pair of atoms. But this was the universe's first true molecule, the inaugural handshake in a chemical conversation that would eventually build stars, planets, and life itself. This entire process was a delicate dance dictated by temperature and density. Had the universe remained too hot, the atoms would have been moving too fast, their collisions too violent to allow for bonding. Had it expanded and thinned out too quickly, the atoms would have been too far apart to ever meet. The conditions had to be just right for this first, fragile partnership to form. The creation of the hydrogen molecule was the universe laying its first, most crucial cornerstone. From this single, simple act, the architecture of everything we know could begin. But that simple hydrogen bond, that first handshake, required a spark. In a universe still cooling from its violent birth, where did the energy come from to push two atoms together against their natural repulsion? The answer might lie in the ghostly, unpredictable world of the very small. At the subatomic level, empty space is not truly empty. It is a seething sea of potential, a constant flicker of energy known as quantum fluctuations. In the incredibly dense early cosmos, these tiny, random variations were not just background noise. They were actors on the stage. Imagine trying to push two powerful magnets together, feeling that force pushing them apart. Now imagine a tiny, invisible hand giving one magnet a random, perfectly timed tap. That is the kind of nudge a quantum fluctuation could provide. These ephemeral bursts of energy could have been the crucial catalyst, allowing particles to momentarily overcome the energy barriers that kept them separate. It was a cosmic gamble, a roll of the quantum dice that occasionally paid off, forging the first stable molecular bonds. This theory beautifully merges the vast scale of cosmology with the intricate rules of quantum chemistry. It suggests that the universe's first chemical reactions were not just a matter of simple collisions, but were guided by the fundamental, probabilistic nature of reality itself. The very fabric of space may have played an active role in writing the first lines of our chemical story. Yet the stage for that first quantum handshake was set by one of the most violent events in cosmic history. An instant after the Big Bang, the universe underwent a growth spurt of unimaginable ferocity. We call this cosmic inflation, a period where space itself expanded faster than the speed of light. This was not a gentle stretching, but a violent, exponential surge that fundamentally shaped everything to come. In a fraction of a second, a region smaller than a subatomic particle was blown up to a size larger than our entire observable universe today. This explosive growth had a profound and direct impact on the potential for chemistry. As space ballooned, it carried the primordial particles with it, flinging them apart. The universe cooled dramatically, and just as importantly, the density of matter plummeted. The once crowded particle soup was suddenly stretched thin. Imagine a pot of boiling water instantly expanding to the size of an ocean. The heat vanishes, and the once colliding molecules are now separated by vast distances. This is what inflation did to the infant cosmos. For any chemical reaction to occur, particles need to meet. The rapid dilution caused by inflation would have slammed the brakes on early reaction rates, potentially delaying the formation of the very first molecules. Yet this cosmic delay may have been a necessary sacrifice. This same violent process also ironed out the wrinkles of the early universe, creating an astonishingly smooth and uniform distribution of matter. Without this large-scale homogeneity, the cosmos might have been a chaotic patchwork of ultra-dense knots and empty voids, a place where chemistry could never proceed in a stable, universal way. So while inflation may have temporarily slowed things down, it also created the calm, even playing field upon which the consistent rules of chemistry could later be written. It was the universe's way of clearing the construction site before laying the foundation. That chaotic plasma was the universe's first and most reactive chemical environment. Before any atoms could form molecules, they first had to be born from a sea of raw, charged particles. For hundreds of thousands of years, the cosmos was not a gas but a brilliant, opaque plasma, a superheated soup where electrons were torn free from atomic nuclei. This state of matter, where particles are electrically charged, is chemistry at its most fundamental and violent. The first true reactions were not about atoms bonding, but about this searing plasma finally cooling enough for those bonds to become possible at all. This pivotal shift is known as recombination, a strangely peaceful name for such a monumental event. As the universe continued to expand and cool, the frenetic dance of particles began to slow. Electrons, which had been wildly careening through space, finally lost enough energy to be captured by the positively charged protons. Each capture created a single, neutral atom of hydrogen. This was not a simple collision. It was a delicate quantum process where an electron settled into a stable orbit around a proton, releasing a burst of light in the process. This released light is the very afterglow we detect today as the cosmic microwave background, a fossilized snapshot of the moment the universe became transparent. This transition from a charged plasma to a neutral gas was arguably the most important chemical event in history. It changed the very nature of the cosmos. A plasma is an excellent conductor, easily tangled by magnetic fields, but a neutral gas is transparent and far more stable. This newfound neutrality allowed the universe to settle, creating the calm conditions necessary for gravity to begin its slow, patient work of pulling matter together into the first clouds of gas. Without recombination, the universe would have remained a blinding, ionized fog, and the story of chemistry might have ended before it ever truly began. But long before that neutral gas could form, the universe had to forge the very cores of those first atoms. The stage for chemistry was set by an even more ancient process known as Bang Nucleosynthesis. In the first few minutes of existence, the cosmos was still a searing nuclear furnace. It was too hot for complete atoms to exist, but it was the perfect environment for the nuclei of atoms to be born. This was not chemistry yet, but the essential pre-chemistry that made all chemistry possible. Protons and neutrons, the building blocks of atomic nuclei, slammed into one another in the incredible heat and density. The first and simplest fusion reaction occurred when a single proton and a single neutron fused together, creating a nucleus of deuterium, a heavy form of hydrogen. This was the crucial first step. Once deuterium was present, a cascade of other reactions could follow. Deuterium nuclei could fuse with more protons and neutrons, building the next element in the chain, helium. For a brief window of about 17 minutes, the entire universe acted as a single, colossal star, fusing the primordial soup into its first elements. Then, as the universe expanded further, it cooled below the temperature needed for fusion, and this cosmic alchemy abruptly stopped. The results of this frantic few minutes were locked in forever. The universe was left with a mixture of about 75% hydrogen nuclei and 25% helium nuclei, with only the tiniest trace of lithium. Everything else, every other element that would later form in stars, was merely a potential dream. This process provided the raw, elemental ingredients for everything to come. Without these atomic cores forged in the fires of the Big Bang itself, there would have been no hydrogen atoms to form the first H2 molecules. There would have been no helium to shape the behavior of the first stars. The periodic table would have been a blank page. Big Bang Nucleosynthesis was the universe assembling its most fundamental Lego bricks, creating the simple but essential palette from which all the complexity of the cosmos would eventually be painted. This simple molecular handshake in the void, however, was just the beginning. The universe was about to discover a powerful new tool for building complexity, a tool born from the death of the first stars. Those early stars lived fast and died young, exploding in spectacular supernovae that seeded the cosmos with something previously rare, heavier elements. From these stellar ashes, the first microscopic dust grains condensed. These were not mere specks of dirt, they were the universe's first chemical laboratories. Drifting in the vast molecular clouds, these tiny grains presented a solid surface where atoms could land and linger. In the emptiness of space, two atoms might collide and simply bounce apart, but on the stable surface of a dust grain they could stick. They could slide along, meeting other atoms and forming bonds that would have been nearly impossible in the open void. This is the theory of dust grain catalysis. Think of it like a dance floor. In the middle of a vast, empty field, two people might struggle to find each other, let alone dance together. But on a defined dance floor, they are brought into close proximity, making connection inevitable. These cosmic dust grains provided that essential stage. They dramatically accelerated the formation of the first complex molecules like water, H2O, and carbon monoxide, CO. A hydrogen atom and an oxygen atom, adrift in a cloud, could independently find a dust grain and wait. When a second hydrogen atom arrived, the ingredients were all present, and the grain's surface provided the energy and stability needed for them to link up, creating a brand new molecule of water. This process transformed the chemical potential of the universe, turning sparse atoms into the molecular building blocks that would one day form planets and, ultimately, the oceans of a world like ours. Yet this delicate chemical dance faced a relentless cosmic adversary. The very first stars did not just forge new elements, they also flooded the cosmos with a searing, invisible rain of high-energy photons, particles of light. This radiation did not build, it destroyed. It ruthlessly broke apart the fragile molecular bonds that had so painstakingly formed in the dark clouds. A newly minted hydrogen molecule drifting through space could be struck by one of these ultraviolet photons. The intense energy would rip the two atoms apart, sending them flying back into the void as solitary individuals. This process, known as photodissociation, acted like a universal reset button on early chemistry. Just as a sandcastle is washed away by the tide, these first molecules were constantly being dismantled. This seems like a purely destructive force, a setback for the emergence of complexity, but destruction can be a strange and powerful form of creation. By constantly clearing the board, photodissociation prevented any single, simple chemical pathway from dominating. It forced the universe to experiment. If one type of molecule was easily torn apart by starlight, then only the more resilient molecules, or those that formed in better shaded environments, could persist. This relentless pruning guided chemical evolution. It encouraged the formation of more complex molecules that were better at dissipating this destructive energy, or that utilized different, more stable atomic bonds. The universe was essentially running countless chemical trials, with the harsh light of the first stars acting as the judge. This brutal selection process weeded out the weak and encouraged innovation, ultimately leading to a far richer and more diverse population of chemical species than if the early cosmos had remained a quiet, dark nursery. The light that destroyed also, paradoxically, taught the universe how to build things that could endure. But the visible matter we have been discussing, the stuff of stars and dust, tells only half the story. Our universe is dominated by a ghost, a substance we cannot see or touch, yet whose gravitational pull shapes the cosmos itself. This is dark matter, and some scientists propose its invisible hand may have guided the very first chemical reactions. While dark matter does not interact with light or engage in chemistry as we know it, its gravity is a powerful sculptor. In the early universe, clumps of dark matter are thought to have formed the first gravitational wells, the seeds of all future structure. Ordinary hydrogen and helium gas, feeling this pull, would have begun to flow into these invisible traps. This subtle herding of the primordial gas could have been crucial. By concentrating the raw ingredients for chemistry into denser pockets, dark matter may have accelerated the entire process. Without these gravitational anchors, the gas might have remained too diffuse for atoms to meet and bond with any efficiency. It is a profound thought that the formation of the first hydrogen molecule in a distant cloud might have been choreographed by the gravity of something we cannot even see. There are even more speculative ideas. Certain theoretical models suggest that some types of dark matter particles could have interacted with normal matter in ways beyond gravity, perhaps through a new, unknown force. While highly hypothetical, such interactions could have provided a tiny amount of extra energy or a catalytic nudge, helping to push those first atoms over the energy barrier to bond. This theory beautifully weaves together the known and the unknown. It suggests that the story of our chemical origins is not just a tale of visible dust and light, but is inextricably linked to the deepest mystery of the cosmos. The universe's first molecular handshakes may have occurred in the shadow of an invisible giant, but forging even that simple hydrogen bond required a specific and unlikely kind of encounter. In the diffuse gas of the early universe, a fundamental problem loomed, a chemical bottleneck known as the three-body reaction problem. For two hydrogen atoms to form a stable H2 molecule, they cannot simply crash into one another and stick. Their collision releases a burst of binding energy, and without a way to dissipate that energy, the new molecule would instantly shake itself apart. The solution requires a third participant, a bystander that can carry the excess energy away. This means that for a brief moment, three separate particles had to meet in the same tiny volume of space at the exact same instant. In today's dense molecular clouds, this is a common event. But in the early cosmos, which was rapidly expanding and thinning out, such a triple coincidence was extraordinarily rare. The universe was an incredibly empty place, and getting three atoms to converge was like trying to arrange a meeting between three specific grains of sand scattered across an entire beach by tossing them into the air just once. This was not just a minor inconvenience, it was a severe limitation that would have dramatically slowed the production of the universe's very first molecule. The pace of early chemistry was held hostage by this statistical improbability. Every successful formation of H2 was a tiny miracle of timing and proximity. This bottleneck forced the universe to rely on slower, less efficient chemical pathways for millions of years, until gravity could eventually pull matter together into denser clouds where three-body collisions became more frequent. The story of our chemical origins, therefore, is not one of rapid, explosive complexity, but of a patient, grinding process where the first foundations were laid one improbable, three-particle handshake at a time. While the universe faced a statistical bottleneck in its empty expanses, a powerful force was brewing within the first great clouds of gas. Supersonic turbulence ripped through these primordial structures, creating a chaotic environment where chemistry could thrive. This was not a gentle stirring, but a violent churning, with shock waves moving faster than the speed of sound through the thin hydrogen and helium gas. These waves acted like immense, invisible pistons, slamming into pockets of gas and compressing them with incredible force. In an instant, a region of sparse, cold gas could be squeezed into a dense, hot knot. This sudden change in conditions was a chemical trigger. The increased density meant atoms were suddenly packed much closer together, making collisions far more frequent. More importantly, the surge in temperature gave the atoms the energetic kick they needed to overcome the barriers to reaction. What would have taken millions of years in the quiet, cold void could now happen in the blink of an eye within these turbulent shock fronts. These were not just random events, they were the universe's first localized chemical factories operating at a furious pace. Picture a vast, calm ocean suddenly struck by a violent storm. The churning water whips up foam and mixes depths that never normally meet. In a similar way, cosmic turbulence did not just compress the gas, it mixed it thoroughly, ensuring that different atoms and simple molecules were constantly brought into contact. A region that was once poor in a certain element could be flooded with new ingredients as a shock wave plowed through it, enabling a whole new set of reactions to begin. This theory suggests that the path to chemical complexity was not a slow, steady climb, but a staccato burst of frantic activity, driven by the chaotic, supersonic weather of the early cosmos. The first complex molecules may not have formed in the calm, but in the storm. Amidst this turbulent cosmic weather, a subtle and elegant chemical shortcut emerged. The universe found a way to bypass the cumbersome three-body problem, relying instead on a fleeting and almost ghostly intermediary, the negative hydrogen ion. This is not the hydrogen atom we know. It is a hydrogen atom that has captured an extra, free-floating electron, giving it a temporary negative charge. In the cooling, neutral gas that filled the cosmos after recombination, free electrons were still abundant. When one of these electrons encountered a neutral hydrogen atom, it could be fleetingly captured, creating this unstable H- ion. This ion was the key. It lived only for a microscopic instant, but that was long enough. The H- ion is highly reactive, desperate to rid itself of that extra electron. When it bumped into another ordinary hydrogen atom, it would instantly donate its spare electron, and in that act of donation, the two hydrogen nuclei would be bound together. They formed a stable hydrogen molecule, H2, and the extra electron was released back into the wild, ready to begin the cycle again. This two-step dance was brilliantly efficient. It sidestepped the need for a rare three-way collision entirely. Instead of requiring three particles to meet at once, the process only needed two separate, far more likely two-body encounters. First, an electron meets a hydrogen atom. Then, the resulting ion meets another hydrogen atom. This pathway likely dominated the early universe, becoming the primary assembly line for the cosmos's most fundamental molecule. It was a chemical sleight of hand, a clever bit of cosmic ingenuity that allowed molecular hydrogen to form in significant quantities, even in the vast, sparse emptiness between the first stars. This simple ion, often overlooked, was the quiet workhorse that built the foundation for everything to come. The universe's chemical toolkit was not limited to ordinary hydrogen. Lying in wait was a heavier, more potent version of the same element, an isotope forged in the Big Bang's very first minutes. This was deuterium, a hydrogen atom with a hidden secret. While a normal hydrogen nucleus contains just a single proton, the heart of a deuterium atom holds both a proton and a neutron. This tiny addition of mass gave deuterium a profound chemical advantage. It could form a unique molecular bond, creating a molecule known as hydrogen deuteride, or HD. This molecule, a partnership between a light hydrogen atom and its heavy deuterium cousin, was far more than just a chemical curiosity. It possessed a special talent that ordinary H2 lacked. When HD molecules collide or vibrate, they are exceptionally efficient at radiating energy away in the form of infrared light. This ability to shed heat was a game changer for the early cosmos. Picture the first vast clouds of gas slowly coalescing under the gentle pull of gravity. As a cloud contracts, it heats up, and this internal heat pressure fights back against further collapse. It is a cosmic stalemate, but if the cloud contains even a trace amount of HD, the molecule acts like a release valve. It efficiently converts the clouds, building thermal energy into radiation that escapes into space. This allows the cloud to cool from the inside out, softening its resistance to gravity's relentless pull. With this internal support system weakened, the cloud can collapse faster and further, reaching the incredible densities and temperatures needed to ignite the first stars. That tiny neutron in the heart of deuterium, a relic from the universe's first 3 minutes, may have been the critical catalyst that tipped the scales, transforming quiet pools of primordial gas into the brilliant furnaces of the first stars. Before the sturdy hydrogen molecule could establish its reign, a far more exotic and fleeting pioneer made the first true molecular bond. This was the helium hydride ion, a fragile union between a helium atom and a lone proton. Its formation was a race against time in the cooling aftermath of the Big Bang. For a brief window, the universe was still a searing plasma, but it was cooling just enough for a few helium nuclei to hold onto their electrons, becoming neutral atoms. Yet the cosmos was still flooded with free protons, the bare nuclei of hydrogen. When one of these fiercely positive protons approached a neutral helium atom, something unprecedented happened. The proton's powerful charge distorted the helium atom's electron cloud, creating a weak but real chemical bond. This was not a simple sharing of electrons like in later molecules. It was a lopsided ionic attraction, the first time two different atomic species had ever linked up. The helium hydride ion was born, the universe's inaugural molecule. Its existence, however, was doomed from the start. As the universe continued to cool and fill with neutral hydrogen atoms, these newcomers proved to be fierce competitors. A neutral hydrogen atom was a perfect match for that lone, bonded proton. The proton would eagerly abandon its fragile partnership with helium to form the much more stable and energetically favorable hydrogen molecule, H2. The destruction of H+ was in fact a vital step forward. By reacting with and neutralizing the last remnants of free protons, it cleared the stage. It removed a reactive species that could have interfered with other, more stable chemical partnerships from forming. The first molecule was a sacrificial pioneer, a bridge between the era of charged particles and the age of neutral chemistry. Its brief flash of existence demonstrated that molecular bonds were even possible, paving the way for the entire chemical universe that would follow. That faint cosmic whisper we detect as the cosmic microwave background is far more than a simple echo of the Big Bang. It is a fossilized imprint of the universe at the precise moment it became chemically mature, a snapshot of the first atoms falling into place. The near-perfect uniformity of this afterglow tells a story of a cosmos that had just completed its most fundamental chemical transition from a searing plasma to a neutral gas. But the story does not end there. Look closer at this fossil light, and you will find faint ripples, tiny variations in temperature no larger than 1 part in 100,000. These minute imperfections are the universe's original blueprints. They are the gravitational seeds, the slightly denser patches of that primordial hydrogen gas where gravity's pull was just a fraction stronger. It was within these specific, mapped-out regions that the entire future of cosmic chemistry was destined to unfold. These density fluctuations preserved in the CMB's pattern were the future sites of the first molecular clouds. The hydrogen atoms that had just formed in the era of recombination were not spread with perfect equality. Where the CMB shows a slightly warmer spot, it marks a region that was marginally denser, a pocket where atoms were packed a little closer together from the very beginning. This increased density was the crucial catalyst. It meant that in these specific zones, atoms collided more frequently. The statistical bottleneck of the three-body problem was slightly eased. The formation of the first hydrogen molecules could begin there first and proceed there fastest. The cosmic microwave background, therefore, is not just a picture of the first atoms. It is a predictive map of where the universe's very first chemical experiments were primed to occur. Those tiny temperature variations imprinted on the sky directly point to the nurseries where molecular hydrogen would first ignite, where gravity would eventually take hold, and where the first stars would ultimately flare to life, forever changing the chemical destiny of the cosmos. Those faint blueprints in the cosmic microwave background, those subtle ripples of density, were the birth announcements for the universe's first true titans. These were the population 3 stars, and they were unlike anything that followed. Born from the pristine gas of hydrogen and helium left by the Big Bang, they contained not a single speck of the heavier elements that fill stars today. This purity made them monsters. Without elements like carbon and oxygen to help radiate away heat, these stars could grow to colossal sizes, some perhaps hundreds of times more massive than our own sun. They lived fast, burning their nuclear fuel with a ferocious intensity, and died young in spectacular cataclysms. But their true legacy was not their light, it was their alchemy. Deep within their cores, these stars became the universe's first true chemical forges. Under crushing pressures and searing temperatures, they accomplished what the Big Bang could not. They began to fuse the primordial hydrogen and helium into new, heavier elements. The first step was fusing helium into carbon. Then, adding more helium, they forged oxygen. In a frantic chain reaction, their cores became factories for neon, magnesium, and silicon, climbing the periodic table one fusion reaction at a time. This was the universe learning to build complexity from simplicity. For the first time, carbon atoms existed, the backbone of all future life. Oxygen filled their stellar hearts, the very breath of future planets. These stars were not just beacons in the dark, they were immense chemical engines running at full throttle for a few million brilliant years. Then came the final act, the supernova. When these giants could no longer support their own weight, they exploded with energy surpassing entire galaxies. This violent death was the crucial delivery mechanism. The supernova blast wave hurled the star's newly forged elements out into the void, scattering carbon, oxygen, silicon, and iron across vast stretches of space. This was the great chemical seeding of the cosmos. The pristine universe was forever contaminated with the raw materials for rocks, for water, for complex molecules, and ultimately for life. Every element in your body besides the hydrogen was forged in a star like this, blasted across space by a long-dead giant's final breath. The age of simple chemistry was over. The universe, now enriched and complex, was ready for its next great act. That chemical enrichment from the first stars set the stage for an even deeper mystery, one written into the very architecture of life itself. All living things on Earth are built from molecules that possess a strange and universal bias, a property known as chirality or handedness. Many complex molecules, like amino acids and sugars, come in two mirror image forms just like your left and right hands. They are made of the same parts, but they are not superimposable. In a lifeless chemical experiment, these forms are always produced in a perfect 50-50 mixture. Yet life, in a stunning act of uniformity, uses only left-handed amino acids to build proteins and only right-handed sugars to build DNA and RNA. This universal preference is called biological homochirality, and its origin is one of the greatest puzzles in science. How did a lifeless cosmos, which shows no inherent preference for left or right, commit to a single-handedness for its entire biological blueprint? The answer may lie not on Earth, but in the hearts of dying stars. When massive stars collapse into neutron stars, they can emit intense beams of radiation. This light can be circularly polarized, spiraling through space like a corkscrew, either clockwise or counterclockwise. This spinning light carries a subtle handedness of its own. As these beams swept through vast molecular clouds in the early solar system, they could have interacted differently with the mirror image forms of prebiotic molecules. One version, say the left-handed amino acid, might have been slightly more stable under a particular polarization, or the other might have been broken apart a fraction more often. Over eons, this persistent, gentle bias from starlight could have tipped the scales, destroying just enough of one-handedness to leave behind a slight excess of the other. Another cosmic culprit could be even more fundamental, rooted in the very laws of physics. The weak nuclear force, one of the four fundamental forces, is the only one that violates mirror symmetry. It has an inherent handedness. On the subatomic level, this force very slightly favors interactions with left-handed particles over right-handed ones. This minuscule preference, buried in the heart of radioactive decay, could have been amplified through chemical reactions. As prebiotic molecules formed and broke apart, the weak force's tiny nudge might have made certain chiral reactions proceed ever so slightly faster, eventually leading to a measurable imbalance. Think of a playground seesaw with a single grain of sand on one side. Left alone, it is perfectly balanced, but that one tiny grain is enough to determine which side will eventually touch the ground if given enough time and a gentle breeze. The circularly polarized light from stellar explosions or the intrinsic bias of the weak force could have been that first, decisive grain of sand. It was not a command, but a whisper, a subtle cosmic suggestion that the early chemistry of our planet heard and then amplified. Once a small imbalance existed, the process of life's emergence likely locked it in, using the slightly more abundant form as a template to build all future molecules. So the very handedness of your body's proteins, the twist in your DNA, might be a fossilized echo of a neutron star's final spin or a fundamental quirk of the universe itself. Even the faintest whisper of a magnetic field could have choreographed the first chemical dances. While the universe after recombination was mostly neutral, it was not completely empty of charged particles. Free electrons and ions still drifted through the sea of hydrogen gas, and these particles are sensitive to even the weakest magnetic influence. The origin of these first cosmic fields is a mystery in itself, perhaps seeded by tiny electric currents in the primordial plasma before atoms even formed. Once established, these fields, though unimaginably faint by modern standards, would have woven an invisible web throughout the cosmos. Charged particles, instead of moving in perfectly straight lines, would have been compelled to spiral along the field lines, tracing invisible paths through the void. This subtle guidance system could have had a profound effect on the earliest chemistry. It would have funneled ions and electrons, steering them toward one another and increasing the likelihood of their collisions. A reaction that depended on two charged particles meeting, like the formation of the helium hydride ion, might have been made significantly more efficient simply because the magnetic architecture of space gently herded the reactants together. The fields did more than just increase the odds. They also imparted a sense of order to the chaotic motions of the early universe. In a completely random gas, particles collide from every possible direction. But when their paths are curved by a magnetic field, their interactions gain a degree of alignment, a preferred directionality. This organization could have influenced the very structure of the first molecules that formed, perhaps even setting a preferred orientation for their chemical bonds as they were born. This magnetic influence extended to the largest scales as well. As gravity began to pull the first gas clouds together, these faint fields were dragged along, becoming compressed and strengthened. They would have provided a subtle backbone to the cloud, a framework that resisted chaotic motions and helped channel the flow of gas along specific filaments. This magnetic support worked against turbulence, creating a more orderly collapse. A cloud that might have simply churned itself apart could instead, guided by these lines of force, flow more smoothly into the dense cores where the first stars were ignited. The presence of a magnetic field essentially added a layer of control to the gravitational chaos, ensuring that the raw ingredients for chemistry were delivered to the stellar nurseries in a more efficient and organized way. The universe's first molecular handshakes, therefore, may not have been purely random encounters. They could have been gently, imperceptibly directed by the ghostly lines of a magnetic map, a hidden guide written into the fabric of space itself. Long before the majestic spiral galaxies we know today, the cosmos was a construction site of a much smaller scale. The first significant chemistry did not wait for these grand designs to take shape. It began in the shadows within countless miniature gravitational traps known as mini-halos. These were the universe's first isolated laboratories, small clumps dominated by the invisible mass of dark matter. Their gravity, though modest, was the first organized force to push back against the relentless expansion of the universe. Within these halos, ordinary hydrogen and helium gas began to pool, drawn in by the silent pull of the unseen dark matter. This was the crucial first step. For the first time since the cosmic dawn, gas was being systematically concentrated. The diffuse atomic soup was being gathered into distinct, denser pockets. In the vast emptiness between these halos, atoms were too far apart to meet with any frequency. But inside, the density rose, turning rare atomic collisions into common events. This compression had an immediate chemical consequence. The increased density made it far easier for hydrogen atoms to find each other and, with the help of free electrons, form stable hydrogen molecules. And the formation of H2 was not the end of the process. It was the beginning of a transformative feedback loop. These newly minted molecules were brilliant at one thing: cooling. As the gas in the mini-halo churned and collided, the H2 molecules efficiently converted the kinetic energy of motion into infrared radiation, which then escaped into space. This loss of heat was like letting the air out of a balloon. The gas cloud, now cooler, could no longer support itself as effectively against the inward crush of gravity. It began to contract further, which in turn increased the density even more, accelerating the formation of yet more hydrogen molecules. This cycle of molecule-assisted cooling and gravitational collapse was the secret engine of the first star formation. A mini-halo was not just a container, it was a chemical reactor whose product, molecular hydrogen, directly fueled its own final act. It created the cold, dense conditions necessary for gravity to finally overcome all resistance. Within these humble, dark matter cocoons, the first protostars flickered to life, their ignition made possible by the simple, efficient chemistry that had unfolded in their cores. The birth of the first starlight was not a sudden event in a random void. It was the final, brilliant step in a chemical process that began in the quiet, concentrated dark of these primordial mini-halos. Carbon, the versatile architect of life, found its first complex expression not on planets, but in the cold void between stars. Among the soot and dust from long-dead suns, a special class of molecule began to emerge, built from rings of carbon atoms fused into elegant, honeycomb-like sheets. These are polycyclic aromatic hydrocarbons, or PAR, and they may have been the universe's first sophisticated carbon-based structures. Tough and resilient, these flat molecules are thought to have been incredibly abundant in the early cosmic environment, forming a kind of molecular scaffolding. Their structure made them uniquely suited for a catalytic role. Picture a bustling train station platform. A pH molecule is like a wide, flat bench where other, smaller atoms and molecules can land and briefly rest. This temporary residence dramatically increases the chance that two passengers will meet and interact. On the surface of a PAH, simple ingredients like carbon monoxide and hydrogen could be brought into close proximity, potentially reacting to form more complex organics like alcohols or even the precursors to amino acids. This was not chemistry happening in a random gas cloud. It was chemistry on a stage with the PAH providing the platform. Their resilience was their greatest asset. The early universe was still bathed in harsh ultraviolet radiation from the first stars, a force that shattered most delicate molecules, but PAHs are notoriously difficult to destroy. Their extensive network of carbon-carbon bonds can absorb the energy of a UV photon and efficiently redistribute it, like a net catching a powerful impact without breaking. Instead of shattering, they simply vibrate intensely and then re-radiate the energy as heat, remaining intact. This durability allowed them to persist where other molecules perished, acting as stable, long-term chemical workhorses in hostile environments. They were the hardy pioneers that could survive the interstellar journey, perhaps even hitching rides on comets and asteroids to eventually seed young planets like Earth with pre-processed organic material. The pH world hypothesis suggests that the path to life's complexity was not a sudden, miraculous leap. It was a gradual, step-by-step construction project, and these robust carbon sheets were the universal building blocks, the sturdy work tables upon which the first pages of the biological story were drafted. Empty space itself may have been the universe's first and most prolific chemical factory. We often think of a vacuum as nothingness, a complete void, but quantum physics paints a far more vibrant picture. According to quantum field theory, the vacuum is not empty. It is a seething, dynamic medium brimming with potential energy. At the tiniest scales and for the briefest instance, this vacuum energy can spontaneously erupt, giving birth to pairs of particles and their antimatter counterparts. An electron and a positron, a quark and an antiquark, could simply pop into existence from the raw energy of the void itself. This is not a metaphor, it is a direct prediction of our most fundamental laws of physics. In the unimaginable density of the early cosmos, this process would have been constant and frenetic. The universe was a bubbling cauldron of spontaneous creation, with particle-antiparticle pairs flickering in and out of reality at a dizzying rate. For the most part, these pairs were ephemeral. They would almost immediately meet and annihilate each other, converting their mass directly back into pure energy in a brilliant, silent flash. This endless cycle of creation and destruction was not a sideshow. It was a primary engine for the primordial heat bath, that searingly hot environment that characterized the universe's infancy. Each annihilation event injected more energy into the cosmic soup, helping to maintain the incredibly high temperatures necessary for the universe to remain a plasma. This process set the stage for everything that followed. The balance between the spontaneous creation of particles and their rapid annihilation helped determine the initial density and temperature profile of the cosmos, the very conditions that would dictate the outcome of Big Bang nucleosynthesis. Had the vacuum energy been different, the rate of this particle production would have changed, altering the primordial recipe. The specific amounts of hydrogen and helium that were forged in the universe's first few minutes were subtly influenced by this ghostly background activity of the vacuum. This theory pushes our understanding to the limit, suggesting that the first chemical ingredients were not just passive survivors of the Big Bang, but were actively shaped by the restless, creative nature of nothingness itself. The void was never truly empty. It was a generative force, setting the initial chemical tone for the entire cosmos through its constant, quiet fireworks. The very existence of atoms and the chemistry they make possible rests on a single, profound cosmic crime. For every particle of matter that was created in the Big Bang, an equal and opposite particle of antimatter should have sprung into existence. When matter meets its antimatter twin, they annihilate each other in a flash of pure energy. If the universe had played by these perfectly symmetrical rules, every proton would have met an antiproton, every electron a positron. The result would have been a final, brilliant flash, leaving behind a cold, dark, and eternal emptiness, a cosmos filled with nothing but fading light. There would have been no atoms, no molecules, no stars, and certainly no one to ponder their absence. The fact that we are here, made of matter, is undeniable proof that the early universe cheated. Something somewhere broke the perfect symmetry. This necessary theft is known as baryogenesis, the genesis of a tiny but decisive excess of matter over antimatter. The question of what caused this imbalance is one of the greatest unsolved problems in physics. The leading theories point to conditions in the universe's first fraction of a second, where extreme energies may have allowed certain particles to decay slightly more often into matter than antimatter. Think of a coin that is perfectly balanced, yet when flipped, lands on heads just 1/1000% more often than tails. Over countless flips, that minuscule bias would eventually lead to a pile of heads and no tails at all. A similar, unimaginably slight preference in the laws of physics must have favored the production of matter. For every 10 billion particles of antimatter created in the Big Bang, perhaps 10 billion and 1 particles of matter came into being. The 10 billion pairs annihilated as expected, but that one lone particle of matter was left behind, a solitary survivor. It is from that 1 in 10 billion remnant that every galaxy, every planet, and every one of us is ultimately built. Baryogenesis was not merely another event in the early cosmos. It was the ultimate prerequisite. Without that initial, mysterious theft, the stage for chemistry would never have been built. There would have been no protons to form hydrogen, no atomic nuclei to fuse in stars, and no periodic table to populate. The universe's capacity for chemical complexity was purchased with that one critical asymmetric act. The fabric of spacetime itself may have been frayed, and those frayed edges could have jump-started the cosmos. Among the most exotic relics of the early universe are hypothetical structures known as cosmic strings. These are not strings in any ordinary sense. They are thought to be incredibly thin, one-dimensional defects in spacetime itself, wrinkles left over from a phase transition in the universe's first moments. If they existed, they would be unimaginably dense, with a single inch of such a string potentially weighing more than a mountain range. Their true power lay not in their substance, but in their gravity. As these cosmic filaments sliced through the primordial fog of hydrogen and helium, their immense gravitational fields would have acted like celestial plows. Any gas they passed through would be violently dragged along, compressed into incredibly dense walls of matter racing outward in their wake. These were not mere ripples, they were gravitational shock waves of phenomenal power. Within these sudden, collapsing fronts, the conditions for chemistry would have been transformed instantly. A region of space that was cold and diffuse could be heated and compressed to stellar densities in a heartbeat. For the atoms caught in this cosmic tsunami, it was a moment of frantic opportunity. The violent increase in density forced atoms into constant energetic collisions. The surge in temperature gave them the energy to overcome the barriers to bonding that would have been insurmountable in the quiet void. The formation of molecular hydrogen, a process that normally depended on slow, statistical chance, could have been accelerated to a blur. These strings were not building molecules atom by atom. They were forging them in vast, productive fronts, creating concentrated ribbons of molecular gas woven through the cosmos. This theory suggests that the first complex chemistry may not have been a universal, slow simmer. It could have been a localized, explosive process ignited along the scars of spacetime itself. The distribution of the first molecules might not have been random, but instead traced the invisible, drifting paths of these cosmic defects, painting the early universe with chemical brushstrokes born from its deepest fractures. This gravitational and chemical partnership created a powerful engine for cosmic construction. The feedback loop between molecule formation and gravitational collapse was the silent, rhythmic heartbeat of the early universe. It began with a simple but profound act, the creation of a single hydrogen molecule. Unlike a solitary atom, a molecule has a special talent. It can vibrate and rotate in complex ways, and when it does, it emits a faint whisper of infrared light. This ability to radiate energy is the key to the entire cycle. In a cloud of pure atomic gas, atoms collide, but they are not as efficient at turning that collision energy into radiation. The cloud heats up, and this thermal pressure pushes back against gravity's pull, creating a stalemate. But introduce even a small amount of molecular hydrogen and everything changes. Each H2 molecule acts like a tiny radiator. When the gas churns and molecules collide, they convert the chaotic energy of motion into infrared photons that simply fly away into the void. A cloud begins to cool from the inside out. Think of a steaming cup of coffee sitting in a cold room. The heat radiates away and the coffee cools down. Now imagine that coffee is a giant cloud of gas in space, and the molecules within it are the ones actively cooling it. As the cloud loses its internal heat, the pressure that was supporting it against its own weight drops. Gravity, always patient, seizes the advantage. The cloud contracts, pulling its gas into a denser, more compact form. This increase in density is the second half of the loop. With atoms now packed closer together, they collide far more frequently. The rate of molecular hydrogen formation skyrockets. More molecules mean more efficient cooling. More efficient cooling allows for further gravitational collapse. Further collapse creates even greater density, which produces even more molecules. This self-reinforcing cycle is a perfect example of a positive feedback loop where each step amplifies the next. It transformed vast, lazy, and diffuse clouds of primordial gas into tightly wound, incredibly dense knots. The loop did not stop until the core of the cloud became so dense and hot that a new nuclear fire ignited, ending the chemical era and birthing the first star. The very molecules forged in the dark cold of these clouds were the catalysts for their own destruction, paving the way for the brilliant, star-filled cosmos we know today. While hydrogen and helium dominated the primordial stage, a third, quieter actor was also present from the very beginning. Lithium, forged in the sparse final moments of Big Bang Nucleosynthesis, existed only in trace amounts, a mere 1 atom for every 10 billion atoms of hydrogen. Yet this tiny population may have punched far above its weight. Lithium is a metal, the lightest and most delicate of all metals, and it possesses a unique chemical personality that could have made it an extraordinary catalyst in the infant cosmos. Its single outermost electron is held only very loosely, making it eager to participate in chemical reactions to donate that electron and form bonds. In the cold, sparse gas where 2 hydrogen atoms might struggle to form a stable molecule, a lone lithium atom could have acted as a nimble intermediary. The theory suggests that a lithium atom could temporarily attach to 1 hydrogen atom, forming a fleeting lithium hydride molecule. This intermediate compound, Li-H, would have been highly reactive. When it then collided with a second hydrogen atom, a sort of atomic handoff could occur. The lithium, having facilitated the introduction, could release the 2 hydrogen atoms now bound together as H2, freeing itself to go and catalyze another reaction. This 2-step dance, mediated by lithium, would have been far more efficient than the rare 3-body collisions the universe otherwise relied upon. Lithium's influence may have extended beyond just hydrogen. Its ions, positively charged lithium atoms that had lost their outer electron, could have attracted the electron clouds of other simple molecules, subtly distorting them and lowering the energy required for new bonds to form. In this way, lithium might have guided the formation of the earliest deuterium-containing molecules or even the fragile helium hydride ion, acting as a universal chemical facilitator. It is a profound thought that this lightest of metals, a mere footnote in the Big Bang's recipe, could have served as the primordial prototype for all the complex catalysts that would later evolve in stars and planets. The chemical processes that now occur in vast industrial reactors or within the cells of living things may have had their first humble rehearsal in the dark, cold reaches of space, guided by the gentle, catalytic touch of lithium. The cold, dark clouds drifting between the stars were far from empty. They were chemical nurseries, quietly assembling the very ingredients of life long before planets even existed. Deep within these frigid, dusty veils, simple atoms of carbon, oxygen, and nitrogen, forged in ancient stellar explosions, began to find one another. Shielded from the harsh glare of ultraviolet radiation, they clung to the surfaces of dust grains, engaging in a slow-motion dance of bond-making. Over millions of years, these humble reactions built molecules of startling complexity. Through the silent language of radio astronomy, we have listened to these clouds and heard their chemical signatures. We have detected the unmistakable fingerprints of amino acids, the fundamental components of proteins. We have found sugars, the energy sources and structural backbones of biology. We have even discovered molecules like ethanol and vinegar floating in these immense interstellar reservoirs. How is this possible in an environment more frigid than the deepest Antarctic ice? The answer lies in the unique conditions of these cosmic clouds. The dust grains act as minuscule laboratories, providing a solid surface where atoms can meet and react. The extreme cold actually helps, slowing atoms down so they can stick together rather than bouncing apart. And cosmic rays, high-energy particles piercing the cloud, provide tiny bursts of energy that can kickstart reactions which would otherwise lie dormant. This theory fundamentally reshapes our understanding of life's origins. It suggests that the universe comes pre-loaded with life's building blocks. The raw materials for biology are not a rare planetary accident, but a common cosmic commodity, manufactured on an industrial scale in the dark between the stars. When a new solar system forms from such an enriched cloud, it is already seeded with these organic molecules. They hitch a ride on comets and asteroids, eventually raining down on young worlds like the early Earth, delivering a starter kit for the chemistry that would one day blossom into life. This means that the path from stardust to a living cell may be a well-traveled road, a sequence of events written into the fundamental chemistry of the cosmos itself. The potential for life is not confined to a few lucky planets, but is woven into the fabric of the galaxy, waiting only for a stable world to provide a home. Far beyond the quiet chemistry of dark clouds, the early universe hosted monsters. Quasars, the intensely bright cores of distant galaxies, unleashed energies that dwarfed entire star clusters. Powered by supermassive black holes greedily consuming matter, these active galactic nuclei, or AN, did not just shine. They ruled. Their influence extended across millions of light years, and they became unexpected architects of intergalactic chemistry. The radiation pouring from a quasar is so fierce it can strip electrons from atoms and tear molecules apart in a process called photodissociation. Near the quasar, space is a sterile desert, a region where complex chemistry is impossible. Yet, paradoxically, this destructive power also creates. The same incredible energy output drives colossal winds and jets of material that slam into the tenuous gas floating between galaxies. These collisions generate immense shock waves, powerful enough to compress that diffuse gas into dense, hot sheets and filaments. In these pressurized cosmic crucibles, atoms are forced together with a violence they would never experience in the calm of a molecular cloud. The sudden surge in density and temperature creates a frantic environment where exotic chemical reactions can occur. Atoms of oxygen, carbon, and silicon, once solitary, are slammed into one another, forming molecules that might be too unstable to form elsewhere. It is a chemical forge operating on an unimaginable scale. One hand of the quasar erases all molecular life, while the other, through its far-reaching shock waves, writes entirely new chemical recipes into the void. This dual role made quasars the ultimate regulators. They ensured that the intergalactic medium was not a uniformly barren wasteland, but a patchwork of chemical deserts and surprising, transient oases where complexity could briefly flourish in the most unexpected of places. This quantum sleight of hand is known as quantum tunneling, a bizarre escape clause written into the laws of physics. In the deep freeze of a molecular cloud, temperatures hover just a few degrees above absolute zero. At such frigid extremes, atoms and molecules move with agonizing slowness, possessing barely a whisper of kinetic energy. According to the classical rules of chemistry, this should bring all reactions to a complete halt. For two particles to bond, they must first overcome a mutual energy barrier, a sort of hill they need to climb before they can link up. In the cold of space, they simply do not have the energy to make the climb. They are like two people stranded at the bottom of a steep valley, unable to reach each other. Quantum tunneling provides a secret passage. At the subatomic level, particles do not behave like solid balls, but like smeared-out waves of probability. There is a finite, if small, chance that a particle can simply appear on the other side of an energy barrier without ever having gone over the top. It does not climb the hill, it effectively digs a tunnel straight through it. This is not a matter of speed or force, it is a fundamental probabilistic quirk of reality. The reaction happens because, for a fleeting instant, the particle's wave function has a tail that extends into the forbidden zone, granting it a ghostly presence where it classically should not be. This process is incredibly slow by terrestrial standards, but on cosmic timescales of millions of years, its effects are profound. It allows hydrogen atoms to slowly, steadily find one another on the surfaces of dust grains, forming the molecular hydrogen that is the lifeblood of star-forming regions. It enables the formation of complex organic molecules in environments we would otherwise consider completely inert. Without quantum tunneling, the dark molecular clouds that dot our galaxy would be far more chemically barren. The rich soup of prebiotic molecules we detect there would be an impossible mystery. This quantum trickle of reactions is the silent, patient chemist of the cold cosmos, working in the dark to build complexity one improbable, tunneled bond at a time. Our universe's chemical laws feel fixed and absolute, but they rest upon a razor's edge. The strength of gravity, the force binding atoms, even the mass of an electron, are defined by a set of fundamental constants. Change any one of these numbers by even a fraction, and the entire edifice of chemistry collapses. This uncanny precision leads to a staggering possibility that our cosmos is just one page in an infinite book of realities. This is the multiverse theory. In this vast ensemble of universes, the fundamental constants are not fixed. They are random, set to different values in each new cosmic bubble. In most of these other realities, the conditions for chemistry would be impossible. Imagine a universe where the strong nuclear force was slightly weaker. In that world, protons could never bind together. The nucleus of a hydrogen atom, a single proton, would be stable, but the next step would fail. Deuterium, the crucial heavy hydrogen forged in the Big Bang, would be impossible. Without deuterium, the chain reaction of nucleosynthesis would stop dead. There would be no helium, no carbon, no oxygen. The periodic table would consist of hydrogen and nothing else. A universe of solitary atoms, forever silent, with no molecules and no complexity. In another universe, the electromagnetic force might be stronger. When two hydrogen atoms approached each other, their mutual repulsion would be so powerful that no quantum fluctuation, no dust grain, could ever push them together. The hydrogen molecule, H2, would never form. Without this molecular coolant, gas clouds could not collapse. Stars would never ignite, leaving the cosmos a dark, perpetual fog of atomic gas. The first chemical handshake would never occur. Our universe seems uniquely tuned for chemistry, a garden in a desert of sterile realities. This fine-tuning is so extreme it begs for an explanation. Is it a cosmic accident, a one-in-a-trillion fluke? Or is it evidence that universes capable of generating chemistry are the only ones where observers can ever arise to wonder about their own origins? The multiverse theory reframes our entire chemical story. The sequence of events from the Big Bang to the first molecule was not just a happy accident in one universe. It was a lottery win in a cosmos where nearly every other ticket was a loser. The very laws that allowed your body's atoms to form and link together might be the rarest exception in a vast and mostly empty cosmic landscape. These ever more complex molecules represent a universe learning to speak a richer language. This leads us to a profound modern idea, the information theory of chemical evolution. It suggests that the entire chemical history of the cosmos is not just a story of new substances, but a story of growing information. Think of the first hydrogen atom as a single binary digit, a 1 or a 0. It is the most basic unit of chemical data. When two hydrogen atoms form a molecule, they are not just bonding, they are creating a more complex message, a simple word in the cosmic vocabulary. Each new element forged in a star, each complex organic molecule assembled on a dust grain, adds another layer of syntax and meaning. The jump from a simple water molecule to a strand of DNA is not merely an increase in atoms, it is an exponential explosion in stored information. DNA is a blueprint, a library of instructions written in a chemical code. So what is the engine driving this cosmic accumulation of information? The laws of physics themselves seem to have a built-in bias. Processes like the formation of stars and planets naturally create systems that are far from equilibrium, and such systems have a tendency to self-organize. They find new, more complex arrangements that can dissipate energy more effectively. A cloud of hydrogen gas is simple, but a star burning that hydrogen is a complex dynamic structure. The chemical reactions that enable this transition are the universe's method of writing more sophisticated software to manage its energy flow. Every time a new, more complex molecule forms, it is as if the universe has discovered a more efficient way to process the fundamental data of existence. This theory reframes our entire journey. The first chemical reactions were not random events. They were the initial lines of code in a cosmic program that has been running for billions of years, constantly expanding its own memory and complexity, building towards the intricate information-rich structures we see in life today. This final theory brings our journey full circle, back to the observers who are here to tell the tale. The anthropic principle offers a profound, if unsettling, answer to why our universe is so exquisitely tuned for chemistry. It simply states that the universe must have properties that allow for the existence of observers, because we are here to observe it. We find ourselves in a cosmos where the strength of gravity was just right to form stars, where the nuclear forces were perfectly balanced to forge carbon in stellar cores, and where the initial density fluctuations were ideal for gathering gas into galaxies. Had any one of these parameters been off by a hair, the chain of events that began with the first hydrogen molecule would have been broken long before life could arise. We do not live in a special universe, we live in the only kind of universe we could possibly live in. This is not a scientific explanation in the traditional sense, but a logical statement about our own place in the cosmic story. The fact that we are here to measure the cosmic microwave background and ponder the helium hydride ion is a direct consequence of a billion-year-long chemical sequence that never hit a dead end. Every theory we have explored, from quantum tunneling in dark clouds to the catalytic power of lithium, describes a universe that is not just capable of chemistry, but one that seems irresistibly driven toward complexity. The anthropic principle frames our entire existence as the outcome of a cosmic selection effect. We are the products of a universe that successfully navigated every chemical bottleneck, a universe where the first handshakes between atoms were not just possible but inevitable. Our very consciousness is the universe's way of looking back on itself, a testament to a chemical story written in the laws of physics from the very first moment. From that first fleeting bond of helium hydride to the intricate organic molecules swirling in stellar nurseries, we have traced a chemical lineage spanning billions of years. This was not a single path but a web of possibilities. The 30 theories we have explored are not rivals, they are collaborators. The quantum nudge of a fluctuation needed the calm stage set by inflation. The destructive power of starlight guided evolution, while the gentle pull of dark matter concentrated the ingredients. The catalytic surface of a dust grain and the ghostly trick of quantum tunneling worked in concert to build complexity in the cold and the dark. Each piece of the puzzle, from the weak nuclear forces biased to the violent forges of quasars, interlocks to tell one grand, unified story of a cosmos learning to build. So we turn this final question over to you. Which of these theories reshapes your understanding of reality the most? Was it the sacrificial role of the very first molecule, or the thought that your own handedness was imprinted by a dying star's spin? Let us know in the comments below, and don't forget to subscribe for more deep dives into the mysteries of the